Welcome to this deep dive. When you think about the microchips inside your laptop or like your smartphone, you probably expect them to be perfect, right?
Right, or like these flawless black boxes engineered perfectly down to the nanometer.
Exactly. But today we're exploring the invisible microscopic world of chip manufacturing, and let me tell you, it is basically.
Even interconnect width and dielectric thickness, they inevitably deviate from the blueprint. It's what we call process variations.
And the thing is, these process variations aren't just like independent random errors scattered everywhere.
No, not at all.
They actually exhibit spatial correlation. So think of it like making a tray of cookies.
Okay, cookies, I like that.
Right. So you put the tray in the oven, and the cookies are not independent of one another. The ones in the back of the oven might all burn together because of like a hot spot,
Oh, I see.
and the ones in the front might all be underbaked together. They share that microenvironment. And in chips, nearby devices correlate much more strongly than distant ones.
That's a great analogy. And understanding why that cookie sheet effect matters is basically the difference between a chip that works and one that completely fails.
Wait, really? It's that drastic?
Oh, yeah. If engineers just assume every component on a wafer acts randomly and completely independently, they're designing for a fantasy world. They miss the reality of that spatial correlation across the wafer.
So, since we know these physical variations are linked, um, how do we actually measure and model them? I mean, we move from the physical wafer to the mathematical solution here, which the presentation calls Gaussian process regression.
Or GPR, yeah.
Right, GPR.
Yeah.
So they feed this model a couple things, right?
Yeah, they take the 2D site locations, so the physical coordinates, and they combine that with actual measurements from multiple independent chips.
And in return, the model spits out three really crucial hyperparameters.
Exactly. You get the length scale, which is basically the correlation range.
Right.
You get the signal amplitude, and finally you get the noise level, which the deck calls the nugget effect.
The nugget effect. Okay, let's unpack this.
Yeah.
Because are we just like drawing a line of best fit through data points here?
What's fascinating here is that it's not just a line of best fit. The secret sauce in GPR is the kernel. And in this context, the kernel literally is the spatial correlation function itself.
Oh, wait. So fitting the Gaussian process isn't just drawing a line. It's like extracting the hidden structure of the correlation.
Precisely. The math mirrors the physical reality.
Okay, but if the kernel is the correlation, what does a kernel actually look like? Because the source outlines a menu of 4 distinct kernels, right?
Yeah, they categorize them along a smoothness spectrum.
A smoothness spectrum. Here's where it gets really interesting, because you can picture these mathematical kernels, like physical terrain.
Oh, I like that visual.
Right, so first you have the Gaussian kernel, which is infinitely smooth. It's like walking over a perfectly smooth rolling glass hill.
No edges anywhere.
Exactly.
Mm.
Then, on the complete opposite end, you have the exponential kernel, which is just rough. It's like hiking over a jagged rocky mountain range.
Every step is a sharp change.
Right. And then in the middle, you have the Matern kernels. You've got Matern 52, which is twice differentiable, and Matern 32, which is once differentiable. They sit on the spectrum between the glass hill and the jagged rocks.
And bringing that terrain analogy back to chip manufacturing is super helpful because a perfectly smooth physical process like chemical mechanical polishing or CMP.
Or optical lithography, right?
Yeah, exactly. Those processes require a smooth kernel, like Matern 52.
Because the physical variation rolls like those glass hills.
Right. But if you have a rough, chaotic process like random dopant fluctuations where individual atoms are just unpredictably distributed.
You need the rough, jagged exponential kernel.
Exactly. You have to match the mathematical terrain to the physical reality.
Okay, but now that we have our mathematical terrain maps, how do we actually calculate this? I mean, doing this across hundreds of chips must be a massive crunch.
Oh, it's a huge computational bottleneck.
Yeah.
Calculating these covariance matrices scales cubically, so standard processors will just melt.
Which is why the text contrasts 2 different approaches.
Yeah. Approach A uses learn GPR. It just looks at a single chip at a time.
Which makes it really fast, I assume.
Super fast. But the downside is it produces a much noisier estimate.
Ah, okay. So what about approach B?
Approach B is multi-realization MLE, or maximum likelihood estimation. This method uses the sample covariance from multiple independent realizations.
Meaning multiple different chips.
Yes, it looks at the whole batch.
But both methods use this optimization algorithm called LBFGSB, right?
They do, yeah.
Okay, so wait. Why do the researchers specifically use a multi-start approach for this algorithm? Like, they start from a default guess, then the true value, and then a totally random point. Doesn't that defeat the efficiency of the algorithm?
You'd think so, but it all comes down to the log likelihood landscape.
The log likelihood landscape.
Yeah, so imagine the optimization terrain has these local minima, basically false bottoms.
Oh, okay. So multi-start is like dropping a bunch of hikers at different random points on a mountain range.
Exactly.
Because if you just drop one hiker, they might walk downhill, hit a false bottom, and stop, thinking they found the lowest valley.
Right, but they completely missed the true, much deeper valley just over the next ridge. Dropping multiple hikers ensures someone actually finds the absolute lowest valley. It makes the extraction totally robust.
And the math really does work. When they tested it against 24 different configurations, the length scale error was under 1.3%.
Which is incredible precision.
And the signal amplitude error was under 0.8%. But that brings up the big question. What happens if the engineers pick the wrong kernel terrain to begin with?
Oh, this is the danger of misspecification, and it is severe.
Because the text highlighted a shocking stat about the Gaussian kernel, right?
Yeah, the Gaussian kernel is by far the most fragile. If you feed it rough, exponential data, the error explodes to 580%.
580%. That's not just a rounding error. That is a complete hallucination.
If we connect this to the bigger picture, the mechanics of why it fails are actually really fascinating.
How so?
Well, if you force a rough process into a perfectly smooth kernel, the optimizer algorithm kind of panics. It tries to stretch the length scale out toward infinity to mimic smooth behavior.
Oh, I see. It's basically trying to cram a square peg into a round hole.
Exactly. And locally, on a tiny section of the chip, that stretched curve might look somewhat okay. But the moment you extrapolate, it completely fails.
So what does this all mean? Like, translate this mathematical failure into a real-world chip design disaster for the listener.
Well, if you overestimate the correlation range by using a rough kernel for smooth data, it leads to over-optimistic timing analysis.
Meaning you think the chip is faster or better than it actually is.
Right, and you put it in a device, push the clock speed, and it just crashes.
And what if you underestimate it?
If you underestimate the correlation, you get overly conservative guard banding.
Guard banding.
Yeah, you essentially over-engineer your safety margins. You end up wasting performance, wasting silicon area, and wasting money for absolutely no reason.
Just because you picked the wrong math kernel.
Just because you picked the wrong kernel.
Wow. Okay, so to prevent these massive miscalculations, the presentation gives chip designers a concrete playbook. And it starts with a magic number of test chips to use, which they call M.
Right, the sample size sensitivity.
So walk us through that. How many chips is enough?
The sweet spot is really between 100 and 200 chips. That gives you reliable data for all the kernels.
What if a team only wants to pay to test 50 chips?
50 is marginal. It might be okay if you're dealing with smooth Gaussian data, but it is extremely risky for rough exponential data.
And under 20 chips.
Completely unreliable, don't even bother.
But wait, why not just test, like, 1,000 chips then?
Because of diminishing returns, the text notes that beyond 200 chips, the error drops proportionally to 1 over the square root of m.
Oh, okay, so it's a huge financial cost for just a tiny microscopic gain in precision.
Exactly, it's just not worth it.
So the ultimate playbook is 100 to 200 chips.
Yeah.
But how do you ensure you don't fall into that 580% misspecification trap we talked about?
The source recommends a really smart cross-validation approach. You basically fit all 4 kernels to your data,
Okay.
and then you compare their log marginal likelihoods, and you pick the winner.
That makes sense. But what if there's a tie, or you just aren't sure?
Well, when in doubt, the source unequivocally recommends Matern 32 as the safest default champion.
Because it sits right in the middle of our terrain spectrum,
Yeah.
right? The once differentiable one.
Exactly. It's highly robust under misspecification, so even if you guess wrong, it won't trigger those catastrophic hallucinations.
Wow. So just to recap this whole journey for you listening, we started in the microscopic, chaotic reality of baking silicon wafers.
Yep, the cookie sheet effect.
Right. And we learned how Gaussian process regression magically turns these scattered data points into structural, topographical maps of correlation.
And we get to walk away with a practical rulebook.
Yeah, which the researchers actually open sourced. It's called the Core Solver on GitHub.
CORR-solver.
Exactly. And the rulebook dictates testing exactly 100 to 200 chips and using that sturdy Matern 32 kernel when in doubt.
You know, this raises an important question, though.
Oh, what's that?
Well, think about the concept of misspecification we just unpacked. The presentation literally proved that when you force a perfectly smooth, idealized assumption, like the Gaussian kernel, onto a rough, messy reality, it breaks.
Right. It wildly stretches the truth to treat and make it fit.
Exactly. It completely destroys its ability to predict the future. So I think it's worth considering. Where else in life or in business or, in data science do we force perfectly smooth assumptions onto a messy, rough reality?
Oh, wow.
And as a result, we end up making these disastrously over optimistic predictions.
That is a great point to end on because whether you're mapping microscopic silicon or mapping out real life, assuming the terrain is smoother than it actually is guarantees you're going to trip up eventually. Thank you so much for joining us on this deep dive, and we will catch you next time.